Hello and welcome to this lecture, which is going to be an introduction to machine learning. The purpose of this lecture is not to actually teach you very much useful information about how to apply machine learning to any specific problem, but instead I want to give you an introduction to what machine learning is all about. I think this is very important because there is a lot of misconceptions out there in the industry among engineers who are not familiar with machine learning as to what machine learning is useful for and how it works. And I hope that this lecture is going to be helpful to give you an overview of the field, but more importantly to understand the basic principles of machine learning and what this set of tools is actually for. First, an introduction to me. I'm Ole Magnus Brastein. I'm, in addition to teaching at the University of Southeast Norway, I work also as a senior R&D engineer and R&D manager at Kelda Drilling Controls. And I am an independent consultant who does various sort of things within software, hardware, and of course machine learning and other advanced algorithms. My background is a bachelor in electronics, where I worked a lot with the dynamic systems, models, firmware, digital signal processing. Then I went on to the industry, where I have about 10 plus years of industry experience as a developer. I did a master's degree in industrial information technology, systems control engineering, where I worked with the different forms of data-driven modeling, such as chemometrics, system identification, some control. And then I went on to do a PhD where I focused on gray box models or stochastic dynamic system models and parameter estimation under uncertainty, as well as machine learning. So two sides of the same coin, really. I've been working as a consultant since 2011. Doing different forms of data-driven modeling, machine learning, cybernetics, Kalman filters, estimation, theory, and so on. I work a lot with different forms of software for industrial applications, both low-level control, firmware type things, but also HMI and different forms of estimation algorithms. I'm pretty much language agnostic, so I program in C, C#, C++, Python, MATLAB, R, whatever the situation requires. I also do some work on sensors and electronics, so hardware, PCB design, so on. I've been in touch with computer vision and robotics on occasion. In Kelda, my main responsibilities or fields is stochastic estimation theory and machine learning, as well as the software engineering, software architecture and design. And also I work in the University of Southeast Norway, where my main tasks is student guidance, teaching, and some research activities. So the agenda for this talk is in part 1 to try to explain to you what machine learning is. In part 2 I will very briefly cover some of the most typical methods and models that are used in machine learning. And in part 3, I will just give a brief overview of various tool sets that you can look up in order to get started with machine learning. As I hope I will make clear in part 1, machine learning is in some sense a very hands-on practical subject. So the best way to learn machine learning is to do machine learning, which is why I think it's important to give an overview of the various tools and frameworks out there that can be used. So then first, what is actually machine learning? Well, the simple answer is that machine learning is computers or machines that can learn. And it's interesting to note that very often when we talk about machine learning, the novelty here is the machine part of things, that we focus on the machines, the programming and the computations involved. But I think it's also useful to notice that we call this machine learning for a reason, which we will see what I mean by that. So machine learning is in some sense a combination of statistics and computer science. And this is evident by the fact that almost all machine learning methods that we use today was invented by a statistician, such as the random forest method, for example, which is one of the most used machine learning methods in the world. That was a statistician who invented that. So I said that we will focus on learning. And when I talk about machine learning, I usually point out the fact that learning means to acquire knowledge. I hope this is not news to any of you, the definition of learning. So it's interesting then to ask the question, why do we call it learning? Well, the machine learning way of working is to learn something from a set of data. And the way we do that is that we extract a model from a set of data. We calibrate the model. And that model is a representation of some underlying knowledge of the system or the mechanism that we wish to study. So the process can be viewed something like this, that we have some kind of a system that we want to study. That can be in the engineering world, typically some kind of dynamic system, a chemical process or a mechanical machine of some description that we want to study. But it can also be something more mundane, like the visual difference between cats and dogs, how they appear in pixelated images, any kind of system, which is basically any part of the physical world that we want to study. And from this system, we then collect a bunch of measurements, which we use to form a set of data or a data set. And from that data set, we then apply the learning process by using a computer, so machine learning. And what we get out in the end is some kind of piece of knowledge which has been encoded in a mathematical way. So it's a knowledge that's described in the computer system. And of course, there is nothing magic to machine learning. When you talk about machine learning to people who don't understand what it is, you get the sense that they believe if you just have enough data and you apply machine learning, then you can fix all the world's problems. And this is, of course, nonsense. Just by looking at this very simple sketch of how machine learning works, I think it's evident that in order to learn something, to extract knowledge from data, that knowledge has to be in the data to begin with. Otherwise, how can you learn? It's kind of like hoping that you just randomly grab a book from a library and learn exactly the information you want to know. Of course, you need to make sure that that information that you want to learn is in the book that you're about to read. Otherwise, the learning process fails. That's exactly the same with machine learning. Unless the knowledge you want to extract is in the data, then there is nothing that can help you. No algorithm in the world can help you. And hence, it's important to put a lot of emphasis into the process of gathering and quality assurance on the data itself. Because if your data is crap, then your knowledge is crap. If you don't pay enough attention to the data collection process, it's like trying to learn something from reading a phone book. It's just a bunch of junk information that can't really tell you anything useful. So I said that machine learning is extracting knowledge, and this knowledge is encoded in the form of models. I don't mean like model trains or catwalk models or any such things. I mean models of the mathematical kind, the ones that we use in engineering. And maybe some of you are familiar with models in the sense of what is typically known as white box models. For example, you use first principles like a mass balance or an energy balance to describe a system with equations and build up a model based on that. This is perhaps the most typical model encountered in engineering fields. And it's interesting to discuss those models as a sort of comparison to what comes next. Because I think it's clear that those models that's described by an expert in the field using physics and mathematics is clearly a type of description of knowledge. I think you can argue that a model describing a process represents knowledge of that process. And it kind of highlights this idea that models are descriptions of knowledge. But the white box model is based on physical insight. It's based on human knowledge. But in the contrary sense, what we are doing with machine learning is often called black box or data-driven models. And those type of models is not based on human expertise or human knowledge, but instead they are representations of knowledge that has been extracted from data using some type of algorithm. And it's interesting to note that these type of models can be, or models in general actually, can be used for two somewhat different purposes. Sometimes we use models for the purpose of forecasting. So we are interested in predicting what a particular system is going to do into the future. But other times we are interested in understanding. We want to use the model to understand how the system behaves. And in the former case, the forecasting case, clearly both of these techniques is very applicable. However, if you are interested in in-depth understanding of the underlying system, then using a data-driven or black box technique can be challenging, because unlike the white box model, which is based on a human description of physics and therefore is very readable, at least to someone who is qualified in the field, the computer-based or mathematical expressions of knowledge that's used in machine learning is very often encoded in a very involved way. It's typically very difficult to look at, let's say, a calibrated neural network and try to extrapolate how the underlying system works. So therefore, there is some resistance against the use of black box or data-driven models in engineering, simply because it is difficult to look at a model and understand how the underlying system works. And that's something which to an engineer is sort of second nature. It's something we like to do. We want to understand the system that we are working on, and it's uncomfortable to use a model as a vital part of some critical system unless we really understand how that model is going to behave. And that's one of the reasons why machine learning is facing some opposition in parts of the engineering community. It's important to keep that in mind. So a little bit more about this concept of models as knowledge. So a model is, as I said, a representation of knowledge of some underlying system. It can be or is formalized in a mathematical language. A quote which supports this statement that models is a representation of knowledge is taken from this famous physics book, Jung. My copy was written in 2000. I'm sure there have been new releases since then, where they state very early in the book, I think it's on page 3, that science is the business of making models. That science uses models to describe the world. So when you think of Newtonian mechanics, Newton's law 1, 2, 3, you can think of those as models of some physical phenomena of forces and accelerations and mass, for example, how these things behave. And even those models, or physical laws as we call them, have limited applicability. We know, for example, that the law of gravity breaks down if you go to quantum levels. Newtonian mechanics break down at very high speeds, close to the speed of light, where you get into relativity territory and so on. And this example shows that we have to be careful when we use models, that we use models within the sort of region of the world where the model is valid. And this is true also for data-driven models and machine learning, that they represent knowledge encoded in a mathematical language, only a slightly different language, as we explained in the previous slides, than the physical models. And we still, in the data-driven sense, have to be careful of applying models, because they are representations of knowledge. They are representing knowledge of an underlying system. They are, of course, not the underlying system. So their knowledge can be incomplete. The first time this concept was introduced to me was a professor who showed this picture, which I have been told says in French that this is not a pipe. Obviously it's not a pipe, it's a picture of a pipe. Just as a model is not the physical system, it is a representation of the physical system, which can convey the knowledge of how the system behaves to a certain extent. So let's look at this process of making models and how we would go about applying that process to a typical chemical process or a plant, as we are often interested in engineering. If one were to write or come up with a model using the traditional mechanistic modeling approach, we would start with balance equations, say energy and mass balance equations. And then we would build our model based on expert human knowledge from those equations. Now, naturally, this requires an in-depth knowledge of how the process works. Otherwise, you cannot express that knowledge because it's your own knowledge that you are writing in equations. However, the data-driven alternative, in contrary to what is often believed, also requires significant understanding of the process involved. Because in order to collect data that covers this information that we want to learn, the knowledge that we want to learn has to be in the data. And therefore we need to understand the process at least to some degree to ensure that we collect the relevant inputs and outputs and information of the system. And then once we are sure that the information we wish to learn is encoded in the data, then we can train the model from data. And that's how we get a representation of knowledge of our underlying system. So I want to talk a little bit more about this idea of forecast versus understanding. And I think this is interesting to philosophize a little bit about this contrast between forecast and understanding, because this goes to the very goal of science. As you may remember, we said that science makes models. And this forecast versus understanding discussion, it's sort of a division that goes back to, let's say, 6 to 400 BC. The ancient Babylonians and the Greeks were both very advanced cultures, ancient cultures, and they were both interested in what at that point in time was scientific understanding and knowledge of the world. But they approached this idea of science, or what we now call science, in very different ways. The Babylonians, they were very good at predicting things mathematically. They used something which is in some sense similar to a Fourier transform, and were able to, for example, predict lunar cycles and eclipses with unprecedented accuracy, according to this book by Stephen Tolmin. It was only almost Renaissance times before Europe caught up to the ancient Babylonian calendar's accuracy for predicting these cyclic phenomena. So their mathematic ability to predict the world was extremely good. But they had no original ideas about the cause of these events. And therefore they tried to use the same methods to predict, for example, earthquakes and locust swarms, something which clearly isn't cyclic. And therefore their predictions miserably failed, because they only had data-driven models. They had only predictive data-driven models, which were very accurate for some phenomena, but their techniques and their methods did not apply to other phenomena, and they didn't understand the importance of this, how these techniques had to be used on a specific set of systems. Now the Greeks, on the other hand, they were much more interested in understanding. So they tried to develop ideas and concepts as to how the world worked. and therefore they could study a whole host of different phenomena, but they were not as good as predicting things as the ancient Babylonians. So their models of the world were perhaps more accurate for some things, but not in the predictive sense. They had a much better understanding of how the world worked. For example, this idea of the atom, as I'm sure you are familiar with. They were able to deduce some very important concepts of how the physics of the world works. But they were not as good at making predictive models. So I think that's enough of philosophy. So let's look a bit at the process of applying machine learning. I talked now about what machine learning is, the importance of understanding what models are, differences between models for forecasting and models that are meant to convey understanding, and this fact that models are used as a form of mathematical encoded knowledge. So if you want to apply machine learning, what we do is always, of course, start with a set of data. And here I have omitted the collection of the data, which is, of course, quite a big sin of omission, because, as I mentioned before, collecting the data is an extremely important part of machine learning. If you don't collect data in a way that ensures that the knowledge you want is in the data to begin with, then all hope is lost. So here we will assume that we now have done our due diligence, we understand the system we are working on, and we have a set of data which is containing some knowledge that we wish to extract. And then we need to do some data pre-processing, which can sort of help improve the quality of the data. We filter out unwanted things, anything that we can eliminate prior to applying machine learning. And only then, once we are sure that we have data of sufficient quality, do we apply an actual machine learning algorithm. So all of this process of doing machine learning is much more than simply applying the algorithm. So it kind of annoys me when someone like MathWorks brags about MATLAB being able to do machine learning in 11 lines of code. Well, yes, that's true. You can train a neural network using MATLAB code in 11 lines of coding. But that's really besides the point, because the hard part about machine learning is not really invoking the framework. The hard part about applying machine learning is understanding everything that goes up to applying the algorithm and understanding the model that comes out of the algorithm. So then once we have applied our machine learning algorithm, we get out some model, which is then, as we have now determined, a representation of the underlying system, of knowledge of the underlying system. And then we can apply some current data, so data from which is not part of the historical data, not part of the data we use to calibrate the model. Then we use current data into the model in order to perform predictions typically about the real world. Because this type of models is typically used for the forecasting or the prediction setting. So let's look at some examples of machine learning. The very first example I usually give is from Google, because they are pioneers of machine learning, and machine learning is kind of in their DNA, so to speak. Because when Google built their search engine, they had a very interesting problem. They were able to find a large number of web pages which contained information about some topic that some user were searching. But as the internet grew, the number of hits became enormously large, and they needed to somehow rate all these web pages to say which of these web pages was better than the others, so that the users of their search engine would get the good pages first. You don't want to find go through 137 pages of junk before you find the information you're looking for. So then it became an engineering question. How do you actually get a search engine to do that for you, to rate web pages, which is described in text in HTML. And that's very not trivial to do that in some sort of rule-based way, that you write rules to say, okay, if the web page does this, then that's a good page. If it does that, it's a bad page. Writing rules in this sort of white box way, equations to calculate if a web page is good or bad, is very, very difficult. However, what Google thought about was using incoming links as data. They understood that by nature of how the World Wide Web works, if some other page linked to, or had a link coming pointing at one of those search page hits to the search, that indicates that some user somewhere on the World Wide Web thought that this particular web page was worth others to read. That's why you link to a page. And the more incoming links a certain page had, the better it probably was, because the more other web designers thought that I want my users to read this particular page. And that's a very good example of how a piece of information, that is the quality of a web page, can be hidden in some particular type of data, which is not really about quality. The number of incoming links doesn't really explicitly state the quality of a web page, but it does in an implicit way convey the quality anyway. And that's a very typical sort of machine learning way of thinking, that the knowledge I want is in the data. I just have to figure out a way to extract it. Now, in this case, it's very simple, because you can just rate all your web pages based on how many incoming links they have. Just sort them. You don't really need to do much modeling to do that. But the key point here is to understand this novelty of the idea that you can use data as a representation of knowledge. And this example also highlights another important concept of machine learning, that in order to do machine learning, you really need to know what you're looking for. You need to understand what knowledge you are searching for. In this case, the quality of a page. And you need to know that this knowledge is in the data that you have, which in this case is the number of incoming links. So a couple of more examples. The most typical example of a machine learning method, I guess, is the email spam filter. That's one of the first examples you will encounter in many machine learning books. An email spam filter, just like trying to estimate the quality of a page, estimating whether a email is spam or not spam based on writing rules would be ridiculously hard. So instead, what we do is we have a learning-based algorithm where some users are classifying emails as either good emails or bad emails. And whenever you get an email which either is spam or isn't spam but is misclassified, you're usually given an option to tell the system that, hey, you made a mistake. This is actually spam, or this is actually not spam. And by doing that, you are adding information to the learning system. You're adding more knowledge to the learning system. And that can help adapt the spam filter to your particular landscape of emails, and therefore improve performance. This is a very typical example of a learning system, where getting more emails and correcting the spam filter helps it to improve its performance, which is clearly a type of learning. Another common example of machine learning is the Netflix-style recommendation systems, which is giving you advice such as, okay, you watched Star Trek, you probably would like to watch Star Wars as well. And that sort of things is based on also on data, on an algorithm which is looking at patterns in consumption of multimedia, consumption of TV and films. And then comparing or extracting knowledge from those patterns and building models of what type of content usually goes together. And then based on your particular preferences, this system can then make predictions as to what other material you may like to consume. And just like all other machine learning methods, this type of algorithms is essentially stupid. They just learn patterns, and they learn the patterns that's in the data. So if you have a very confusing Netflix habit, in my case, I have 4 children, so sometimes they use my Netflix account. So even though one day I'm watching Star Trek, and the next day it's Peppa Pig, and then it's Star Trek again, and then some other childish cartoon, that sort of thing can make Netflix recommendation systems very confused, because there is no clear pattern in what I'm watching. And then they're trying to work around that by adding multiple user accounts and so on per subscription. But in essence, it highlights a problem with machine learning, that if the machine learning algorithm assumes that all the data it collects on a particular account is only for one user, and that assumption doesn't hold, then you can end up with making very serious mistakes. Of course, for the Netflix system, that's serious mistake might result in Netflix suggesting that I watch Peppa Pig on a Saturday afternoon, but that's fine. It doesn't hurt me very much. But imagine an F-16 fighter jet based on a machine learning algorithm, which would do some silly mistake like that. It could be critical, which is why we don't typically use machine learning methods in anything that cannot fail. I'll get back to that point later. Some other examples of machine learning is playing games. I'm sure you are familiar with some examples of this. Much of the development of AI and machine learning has been focused around different types of playing games. And one example or two examples of this is the games chess and Go. Both, of course, are board-based strategy games, where chess is the simpler one, and was also one of the first sort of challenges that was attacked by the machine learning and AI community. And one of the early breakthroughs for research into AI and machine learning was IBM's Deep Blue computer, who defeated Garry Kasparov in 1996. And it's worth noting that this particular software, the Deep Blue computer, was an AI. It was based on numerical optimization or tree search, but it was not really based on learning. So it was not really a machine learning application. There has been, of course, machine learning applied to chess as well, but the best chess engines now in the world, they still do mostly tree search. And because computers are so fast, things like Stockfish chess engine, there's no human in the world who can beat those simply by brute force computation in tree search in clever ways. So chess, from a science point of view, is kind of a solved problem. The state-of-the-art chess engines is undefeatable by humans. And the reason for that is that chess is relatively simple. The number of possible games you can play is 10 to the 123rd power, so a 1 with 123 zeros behind it, which is a search space that is manageable by today's computers. And therefore, when they wanted to apply machine learning to strategy games, they shifted focus to Go, which has 10 to the 360 number of possible games you can play. So an enormously more large search space. In fact, this is a number bigger than the estimated number of atoms in the entire universe. So it's an enormously large search space. In fact, it's so large that it's unlikely to ever be invented a computer that can handle a search space like that. And therefore, the only way you can really play Go is using some kind of learning approach, because you cannot simply just compute your way out of the problem. This is what Google did with their DeepMind AlphaGo and AlphaGo Zero, which is based on deep learning and neural networks. That is a machine learning application used at games. Maybe some of you are familiar with this story, that they played the world champion and they eventually won. It was quoted after that match that AlphaGo played many unprecedented, creative, even beautiful moves in Go. And the guy who actually played this computer said that it was like playing an alien, because the computer didn't think like any human he had ever played against. But of course, Google, they like playing games, so they decided to use their machine learning game playing engine on chess as well, even though I said chess is sort of a solved problem. But they then used their AlphaZero engine, which is the evolved sort of DeepMind architecture, and they taught this engine to play chess simply by playing chess with itself for 4 hours. For those of you who remember movies from the 1980s, there was once a movie called War Games, in which two supercomputers, or a supercomputer was given control of the US nuclear arsenal and was about to start World War III. And the way they sort of taught the computer that this is a bad idea was having it play games against itself. I'm not sure if that's where Google got the idea, but I don't think scientific exploration and nuclear holocaust should play together too much. But anyway, this is what Google did. They let the computer play chess with itself for 4 hours. And in those 4 hours, this AlphaZero network learned to play chess so well that it defeated Stockfish 64-36 in a set of 100 matches. And for those of you who follow chess, you will know that beating someone 64 wins to 36 draws, that is an extremely strong victory. Usually in chess, when you play high-level chess, it ends up in draw. Most games ends up in draw. So beating someone 64-36 with 0 losses, that is an extreme achievement. And bear in mind that this is against Stockfish, which was considered a state-of-the-art chess engine. And this engine has defeated people like Caruana, who is one of the best human players in the world. A little bit about industrial applications also, because machine learning does indeed have applications in the industrial world, which is interesting for us engineers to know about. So there are examples of systems where doing any kind of physical modeling is simply impossible. One such example is very, very difficult nonlinear systems, or identification of very difficult nonlinear systems, where the traditional system identification techniques doesn't work because they tend to assume linear state transitions and so on. There are some interesting applications to machine learning there. Very complex chemical and biological processes, where it's also one common application for machine learning. And in general, modeling of systems that cannot be very easily described by mechanistic equations. So one example of such systems, which is instructive, is systems for what we call predictive maintenance. And predictive maintenance is very often based on trying to measure vibration patterns or sound, noise, that an engine or a machine makes, and then trying to estimate the condition of the machine. And the idea is actually very intuitive. Experienced, seasoned mechanics, they use their hearing a lot. They listen to the sound cars and machines make, and then from that sound they can induce if the machine is working as intended. And the idea of this acoustics-based predictive maintenance is to basically learn the knowledge that it requires to listen to the sound of an engine, which you can easily do with an accelerometer and an FFT algorithm, and then try to extract the knowledge from those sound spectra of when the machine is in good condition or when it's about to go wrong, and then use that predictions in order to know when you need to stop the machine to do maintenance and so on. And it's easy to understand that it would be very, very difficult to write a mechanistic model which correlates sounds and frequencies to the condition of a mechanical machine. But it's actually very simple to record the sound and create data sets of it, and then tell the system which of those sounds correspond to a machine that is okay, and which sounds correspond to a machine which is in some way about to break down or has broken down. And then the algorithms can help us figure out the correlation between machine condition and the sound it makes. One further example, which is similar to this acoustics predictive maintenance approach, is something called densitometry, or dual energy gamma densitometry, which is based on using gamma radiation and typically applied to what we call multi-phase flow. That is some pipe or some container which has both water, air and oil in it, or gas, oil and water, and then trying to estimate the volumetric fractions of each of these three phases, and preferably also estimate the flow regime, that is to estimate how those three phases are distributed inside the pipe. And the way this works is that the attenuation of gamma radiation is different for each of these three phases. So by irradiating photons through these containers and counting the number of photons that comes out on the other side, we can create a data set which can then be used as a spectra. And then we use machine learning to learn the knowledge that it takes to estimate volumetric fractions from photon counts. There has been some interesting work almost 30 years ago already on using neural networks to figure out volumetric fractions from this gamma densitometry spectra. And an interesting observation here is if you read this paper by Bishop and James. This guy Bishop, by the way, he's now one of the main machine learning guys in the Microsoft companies. So he has had a good career in machine learning since writing this paper. He's a famous machine learning guy by now. He wasn't that famous in '92, but he is now. And his paper, they discuss a lot the physics of the system and the placement of these gamma radiation beams. So they are very well aware that in order to get anything reasonable out of a machine learning method, you really have to take care of the data collection. So for example, they have this cross pattern that they have both vertical and horizontal gamma radiations in order to capture, for example, this flow regime which is called stratified flow. So if you only had horizontal beams, then there's no way you could do any kind of quantitative measurements on stratified flow, because you would see then only water from one beam, only oil from the third beam, and perhaps only gas from the last beam. So you really have to understand the physics of the process you are studying in order to successfully apply machine learning, something which this article highlights very well. But they don't actually use the physical equations here. It's just the understanding of the process that's applied. So now I talked a lot about learning from data, and perhaps some of you are wondering or have heard of other techniques to do data-driven modeling. I mean, I said before also that most of machine learning techniques have been invented by statisticians, and statistics is also in general concerned with making models from data. So there are lots of techniques out there that does something similar to what I've been talking about, which is extracting knowledge from data. And one question that is very often asked is, but what makes machine learning then different from everything else that tries to extract knowledge from data? And one way to answer that question is that it really isn't that different. Machine learning is just statistics and computer science merged together. But there are some things which I think is what one might consider demarcation criteria for a machine learning method. And one such, I think, common trait with algorithms that we typically think of as machine learning is that there is a certain freedom to be creative when you design a method. So if you compare something like a decision tree, which has this very simple structure of asking questions and then checking the answer, and then stringing together more questions in a sort of a tree-like structure. So this is sort of an upside-down tree. And this structure is sort of inspired by branching, the way nature works. Trees and tree search and branching is used in a lot of different ways in statistics, but in this particular case, it's a decision tree. It's modeled after how nature works, that you have branches, things that sort of spread out the further up or down the system you go. And if you compare that to something like the principal component analysis, the method of PCA is very much based on mathematics. There is mathematical proofs and evidence and derivations that show in what sense these PCA components are related to data. It has a very strong mathematical basis. And this is different than this machine learning approaches. So one can say that this machine learning methods, they are often, as with the decision trees, very simple concepts, and they tend to be inspired by nature in some way. Not always, but in the general sense. And they are typically not very theoretical. You don't usually find machine learning techniques derived from some complex mathematical evidence and then evolved into a working method. It's usually the other way around, that you start with some simple concepts and then you can apply a lot of very difficult and strong theoretical analysis to those simple concepts in order to get them to do something useful. Another thing is that machine learning, or the model structures that we use in machine learning, tend to be very complex nonlinear model structures. So although the individual components is simple, like these decision trees, for example, where it's just questions and answers, you can imagine that if you have hundreds of these questions stacked on top of each other with maybe thousands or millions of possible routes through this tree, that becomes a very complex structure. And on top of that, you very often have multiples of this tree. So you don't just have one such tree, you have maybe a whole bunch of them that form a model put together. And then it becomes a very, very complex nonlinear model structure, which is very hard to analyze theoretically, very hard for a human to understand and read. But for a computer, that's not a problem, because each little piece of the model is simple and therefore fast to compute. So having a high number of them doesn't necessarily pose a problem for the computer. That brings us to this implementation of the computer science part. So rather than what we do in things like system identification or chemometrics, or indeed the Kalman filtering for state estimation, where we use mathematics up front to simplify the problem down to something which is easy to implement. Instead, in machine learning, we turn this upside down and we use very simple descriptions of the real world, such as decision trees or neural networks. And then we put the emphasis on the implementation instead, and we put the effort into the computer science that makes these simple concepts operate and do something useful. So I want to say also a little bit about this idea of complexity of models. So like I said in the previous slide, that a key demarcation criteria for machine learning is that the model structure tends to be very complex. And this is part of the reason why machine learning is as powerful as it is. Because this complex model structures provides us something which we call description power, or the ability to describe complex phenomena. But this is not something which is unique to machine learning. You can even show this with something as simple as sort of curve fitting or regression type models. So if you have these black points here, which represents our data, and we try to adapt some kind of polynomial to these data points, you can very easily show that if you try to do that with, for example, a second or first order polynomial, so you have y equal to ax plus b, then you would get a straight line, which in this case is a pretty poor fit to the data points. But then you can extend your model in complexity by adding another parameter to get a second order polynomial, which is this green line here. And if you do that, then you get a slightly better fit to the data. But if you go to, let's say, a third or fourth order polynomial with respectively 4 or 5 parameters, then by gradually increasing the complexity, you get better and better fit with your data. And that's exactly the same effect. That the more parameters you have, the better description power your model has, and the more complex patterns in data is your model able to learn. Now, of course, this sounds very nice. You can just use complex structures and implementations and programming and then get something magic out of that. But of course, there is never such a thing as a free lunch. Since machine learning is so based on these complex model structures, and also, as I mentioned, it tends to be based on these simplistic model structures without a deep theoretical basis, it's very often difficult to suggest optimal tunings. There's been a bunch of papers written about trying to suggest optimal neural network structures and rules of thumb for how to tune and configure neural networks or other machine learning methods. And all these rules of thumb, they have usually one thing in common, that they don't work. They work for specific sets of problems, but not in general. And the reason is that since there is no theoretical foundation for claiming optimality, for example, of a neural network, it's probably impossible to come up with general rules on how to tune a machine learning technique. Instead, it really requires hands-on experience. It requires the engineer's touch. It requires somebody who has spent hours and hours and hours fighting with hyperparameters and trying to come up with some sort of optimal network structure for a neural network in order to build good models. And that is, in general, time-consuming and challenging work, but it is something that you can learn. It's a craft, in a sense, to do that. And although it can be very time-consuming to calibrate models and search for good tunings and hyperparameters, once you actually have a working model, these models are usually relatively fast in forward execution because each of these components is very simple. So, for example, in the decision tree, then evaluating whether a specific set of input data from the process answers the questions yes or no, or true, false, or whatever the questions may be. But figuring out the answer to these split nodes in the tree is usually very fast. Or in the case of a neural network, then the forward pass is quick, because the computations is very simple. It's the training and the calibration of the model which is very time consuming. And finally, as I have said now repeatedly, since machine learning is black box modeling, then data is all we have, and therefore we are bound to this rule that the data must contain the knowledge that we are trying to extract. And that is the problem, which is, well, when you collect the data and you control the data collection process, then you can in some degree ensure that this is the case, but it's not always so easy to be sure that the knowledge you are looking for is actually in the data. Sometimes you can spend months collecting data and calibrating models and nothing comes out. You don't learn anything. You don't come up with any working models at all. So just to say a little bit more about this importance of data. Common quote is Sherlock Holmes, for those of you who are interested in 18th century literature. Data, data, data. I cannot make bricks without clay. That was, of course, said about deductive reasoning, as Sherlock Holmes was known to apply, but it is just as important for machine learning. And the first thing which is important to understand is that you need data that are relevant. That means the right data. You have to collect data which is containing the knowledge you want. And that does require some understanding of the process that you are studying. You really need to understand the system that you want to build a model of, and you have to ensure that the data you collect is relevant for whatever phenomenon you are studying. Another keyword is that you need data which is complete, in the sense that it covers all the system states that you are looking for. An example of that is in error detection. If you want to detect when a system is about to fail, then it really doesn't help to have all your data from a system which is in perfect working condition. So let's say if you want to build a model that can detect failure of a train track or something like that, then you actually have to drive the train over the faulty track repeatedly to collect information about when the system isn't working. And that can be very difficult because in many cases when you have a system that is not in working order, data collection is very low on the list of priorities of whoever owns the machine. They usually want it fixed right away, and it can be very challenging for data scientists to be allowed to collect the necessary information, necessary data from a system in default state. And finally, the last keyword is sufficient, that we need enough data. Machine learning is notoriously data hungry. You can never really have enough data. Of course you can, because there are limits to how much data you can use. But having sufficient amounts of data is important because of something called overfitting, which we will get back to later. But just how much data is needed, that really depends on the complexity of the system. So it's difficult to say exactly how much data is really required.